The next section is stellar radiation and stellar types. We have to state that fusion is the main energy source of stars. Fusion is when small nuclei come together to make a larger nuclei, and they release lots of radiation energy. In this case we have hydrogen. For most stars, hydrogen is converted into helium. Now, how do stars start to fuse? Basically, we start off with an interstellar dust cloud, which starts to come together by its mutual gravitational attraction. As it comes together, the potential energy, the change in potential energy, the loss in potential energy is turned into kinetic energy as the particles speed up. And since temperature is a measure of the average kinetic energy, we lose potential energy, you gain kinetic energy. In other words, you increase the temperature. Eventually, the temperature is high enough for fusion to start. Now, fusion produces so much energy that it gives off a great deal of radiation energy. And as you know, photons can have momentum. So basically, we have the radiation pressure from the fusion, which supports the star. So we have two forces in opposition: gravitational pressure and radiation pressure. So in nuclear fusion, normally in the center of stars, you need a temperature of roughly 10 to the 7 Kelvin, 10 million Kelvin. You need these to have these high pressures, high temperatures, so the particles are moving fast enough to overcome the electrostatic Coulomb repulsion. We have two hydrogens fused together to produce deuterium, which is a heavy hydrogen. This could, for example, join with another hydrogen and produce two protons and one neutron. This is a light nucleus of helium, helium-3. These two heliums fuse together and they make helium-4 and produce two hydrogens. So basically we have this is the stages of one of the possible stages for fusion to take place. And this happens in the center of the star. So a star is basically you basically have a core which is hydrogen burning, and outside which is a hot hydrogen but is not high enough in temperature for fusion to take place. As I said before, in a stable star there's an equilibrium between radiation pressure and gravitational pressure. So this is the star. We have gravitational pressure. We know that the center of the mass is here, and gravitational force will be pulling all the gas towards the center. But due to the nuclear processes that are taking place in the center, these photons, which are momentum, are supporting the weight of the outside of the star. So we have basically what's called radiation pressure. If radiation pressure and the gravitational pressure are equal, then we have an equilibrium. What is the most important thing about a star? It's basically its mass. The mass will determine pretty much everything to do with a star. It determines its luminosity, how bright it is, and it determines its temperature. When I say a normal star, it's the hydrogen burning part of the star, the hydrogen burning part of its life process. Later on, when it gets towards the end of its life, it starts producing burning other elements. But first of all, for the main part of the main sequence, the main part of the star's lifetime, it burns hydrogen. Define the luminosity of a star. Well, the luminosity is how much energy is given off per second. That's it. Energy per second is the number of watts given out. A light bulb, for example, is a 60 watt source. Its luminosity is 60 watts. The energy of the sun is basically generated by fusion, which happens in its core. So what does the luminosity have to do with the mass? Well, the mass of the star determines the pressure. The larger the pressure, the greater the mass. So if there's a large pressure, greater mass, you can have a much higher temperature, higher pressure, higher temperature. And if that happens, then you're going to get, if the pressure is and the temperature is higher, the rate of fusion is going to be higher as well. So if you increase the mass, you increase the pressure and the temperature, you will increase the rate of fusion. And if the rate of fusion is much faster, much higher, then the luminosity will be greater. So a large mass will mean a very luminous star. In fact, we can look at the relationship between the mass and the luminosity. As you increase the mass, you increase the luminosity. In fact, the relationship is basically this: the luminosity of the star is proportional to the mass to the power of 3 or 4. Now it's somewhere between there. So in other words, if you double the mass of the star, the luminosity is going to be double cubed. In other words, 2, 4, 8 times as bright, or it could be 2 to the 4. It could be 16 times as bright. So in other words, you double the mass of the star, the luminosity is going to be between 8 and 16 times brighter. So the luminosity is basically how much energy is given out by the star. Now, wherever you see the star, from wherever its luminosity will still be the same. But if it's far away, it will not appear to be so bright. So we have this another thing which is related to the luminosity, which will also depend on the distance, which is the brightness, and we'll look at that now. So at first, we cannot determine the luminosity of a star if it's far away. An apparently bright star might be a dim star but very close. But you know, the song goes, "Twinkle, twinkle, little star, how I wonder what you are." If you look at the spectrum of a star, you can basically find out everything to do with a star. You can find out its luminosity, you can find its temperature, its mass, its radius, the distance from us, the age, its life expectancy, and so on. You can find out everything just by looking at the spectrum of a star. Everything is linked to everything else. So the luminosity. The luminosity of a star is the energy that it releases per second. We know that the sun has a luminosity of roughly 4 times 10 to the 26 watts. In other words, 4 times 10 to the 26 joules per second in all directions, if you add all the energy up. The energy that arrives at the Earth is only a tiny portion of that, because we're so far away that energy spread out by the time it reaches us. So we look at this thing called brightness, or apparent brightness. Now, this radiation that's given out by the sun is spread over the whole sphere here, but we only get a small part of it. Only the energy that gets spread over this area of the Earth is going to basically how we define the brightness. So the brightness is the luminosity, which is the total luminosity which is given out by the sun, divided by 4 pi d squared, which is the area, the complete area of the sphere, which is the sphere of radiation, which is at the distance of where the Earth's orbit is. And this is how we define the apparent brightness of a star. So to find the brightness, what will it be? What will the units be in? The luminosity is in watts, 4 pi d squared is in meters squared. So the brightness will be so many watts per meter squared, and we'll find out what that is. The sun is a distance of 1.5 times 10 to the 11 meters from the Earth, so we can calculate the brightness. In other words, how much falls on 1 meter squared of the Earth's surface. The luminosity is 4 times 10 to the 26 watts, divided by the area of this, which is 4 pi d squared. So the Earth's surface is 4 pi d squared, which is this value. The luminosity, the brightness, is the luminosity divided by the area, which is 4 times 10 to the 26, divided by the area of this sphere of radiation at the Earth's, where the Earth is, at this radius here. And we end up with a value of roughly 1,400 watts per meter squared. In other words, on the Earth's surface, where it meets the Earth's surface at 90 degrees, the radiation brightness will be 1,400 watts for every square meter. And you can find out how much energy is going to fall on 1 square meter during the whole year. This is the 1400 joules per second, so you mind the number of seconds in the year, so it's going to be 365 times 24 times 60 times 60 times that value of 1400 gives a value of times by 1400 gives a value of 4 times 10 to the 10 joules of solar radiation. It falls on 1 square meter in 1 year.